Hello everyone, welcome back to the channel. My name is Sachit and today we will be going to discuss problem number 211. The problem statement is as follows. We have to design a data structure that supports adding new words and finding if a string matches any previously added string. Okay, so to implement that we have to fill the class word dictionary which has three given functions to us. The constructor for that class, the add word function, then the search word function. In the search word function, it mentions that the word we have to search, it may contain dot, which essentially means that it can replace any characters. And now it has also mentioned us an important constraint that the word in search consists of dots or lowercase English letters, which are from A to Z. That is, we have only 26 possible cases for dot that we have to consider. Now, one basic solution can be using maps. So what can that be? Let us see. And why will that given TLE? Let's also see that. If we use, maps in C++ or any other language you use, so basically what the problem will be that let us say we have to search a word such as this h dot 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 r. Okay. Now the problem with maps is that okay, I have stored all the previous occurrences at whichever word we were given, but for each dot I have 26 possible combinations to consider, right? So for this case, I will need to consider 26 to the power 3. For each dot we have 26 cases, right? And that for each case I will have to go and check in the map that is this present or not, and if I find any one case I output true. You know, so the good case can be that the first letter, first combination we check is present, but the worst case can be that a 26 to the power third combination. Till that point we have to check and still we don't find the answer. And now why does the optimized solution can be using try. I am assuming that you know basics of what a try data structure is. Okay, so if not, I will be explaining it a bit further. So what does try helps us in reducing the time complexity is it essentially checks that okay, like for the first dot, if I am taking a, then try will check that okay, if ha is present in the try, basically if there is a word in the list which starts with ha, then only it will let me allow to process the further combinations. But in a map, we cannot check that if hey is a word starting with HA. But in a try, we can do so in O(n) time complexity. But in map, we can't do so. So now coming back to why, how a try data structure works, let me just quickly switch to a document. So what is a try basically? Try is a tree that has a root node, and for this problem, each node can have up to 26 children, which are lowercase characters from A to Z, and each node will represent a single character. So let us have a look at this diagram to make things more clear. In this, I created a try for a list basically containing words whichever are marked with star. Okay, deal, dear, do, heal, hen, all these, whichever are marked with a star. After that, we can see that for inserting deal, what I have done is I first inserted D, then DE, then DEA, then deal. Similarly for dear, for do, for heal, for n. So let's say that I have inserted heal. Now I wanted to insert hen. And what will I do? I will first check that from the root node. Okay, do I have an H? I have an H. Do I have an E? I have an E. Do I have an N? I don't have an N. So first I insert an N and then I insert it into my data structure hen. So that's how we will be proceeding. First of all, I have created a try class which will be having the children as we discussed, and each node will be having a property is end. That is this node ending any string. For example, if I see for this character HEA, the A is the A ending any string? No, HEA is not a complete string, right? So it is end will be false. But for HEAL, it's a complete word, right? So that's why I marked it with a star, or in our code, we will represent is end variable to show that, okay, this is a complete word and L is marking an end of a character. And similarly with he, fit, do, fit, deal, and dear, and so on. Okay, after that, I have used the constructor to initialize this. Initially the isNt will be false and the children will be null pointer because we don't have anything in the node. After that, for a word dictionary class, I have added some variables to it. First of all, the root node, as I said before, and the word dictionary constructor class which we had to implement. I am just making the root node point to a new node of the try. After that, let's see for the add word class. So first of all, I just created a temporary variable to store the root node, and then I'm traversing the word string, and I'm checking that, okay, first tell me that does, let's say our word was in this case only, let's say we have to insert the word deal, then I'm first traversing over deal and I'm checking that d minus a, which will be the children of fourth. Basically we have stored in 26, right? So we have to check like 1 2 3 4, and the d will be the fourth in the sequence. Okay, so I'm checking that is it null. If it's null, then insert it and assign it a new node. If it's not, basically it's already present, then we are saying that okay, move temp to that already present node and check again for the next character. So basically we are saying that, let's say if I had already done with deal and I'm on dear, then we have already have D. Okay, then we move to the next node E. We already have E. Then we already have A, and then we check that do we have R. We don't have R, so we create a new node and insert it. After that, all we just what we do is that we mark the is end to be true. That okay, we have reached the end of the word. So whichever node is there, mark it as true. So that will be the very simple implementation of add word class. Now, if we have to do it for search, initially we were given something like this. Now I returned my own constructed search function which takes the word and it takes the parent. Now what's this parent is just the root node, and as we were discussing in the add word class, the which parent is for whichever you are comparing the children of it, right? So similarly, first we are traversing the whole word string, and then if the word of I is equal to dot, which means why I am using a for loop is here because I need to check for all 26 combinations, right? So first of all, I am checking, as I said in the starting, that hey, is the temp children of J? Basically, if J is 0, it means A. If J is 1, it means B. So I am checking that hey, if the current word plus A, if this exists in the try, only then search. So this helps us in reducing a time complexity over the map method of doing this problem. Okay, so in the search function I am providing the next part of the word, substring I plus 1, and for the parent I am providing the current node which I just took to as the next word, temp children of J, and if I find, I return true. And if after the for loop I have checked for all possible combinations and none of them satisfied, I'm straight away returning false. And now if the word I was not equal to dot, it was some constant word which we know, then I'm just doing that, is that is that character present? If it's not present, then just return false, because it's obvious, right? Let's say I'm searching for deer, and if D is present but E is not, then there is no point to check for A and R, right? So that's why I straight away return false. And if it's present, then I simply move on to that node, and the recursively this process gets called and called. After that, when I have done with the all the word length, what I do is I just return that okay, I reached the end point. Now to check the last condition, if that complete word was a word, actual word or not, or was just a part of some other complete word. Basically, if we were checking for DE, then okay, DE is present in the try, but it's not a complete word in itself. It's a part of deal, which was a complete word. So that we have to check, and then we will return it, and that's it. So this should pass all the test cases. Let me see. Okay, there we go. Thank you. That's it from my side.